that told me I never amount to nothing. All the people that lived above the buildings that I was hustling for, they called the police on me when I was trying to make some money to feed my daughter. To all my peoples in the struggle, you know what I'm saying? It's all good, baby. It was all a dream. I used to read Word Up magazine, Salt and Pepper and Heavy D up in the limousine, hanging pictures on my wall. Every Saturday, rap attack, Mr. Magic Molly Mall. I let my tape rock till my tape hot. Smoking the bamboo, sipping all private stock. Way back when I had the red and black lumberjack with the hat to match. Remember rapping Duke? The hard. You never thought that hip hop would make it this far. Now I'm in the limelight cause I rhyme tight. Time to get paid, blow up like the world trade. Born sinner.
Morning, everyone.
I'm a winner. Remember when I used to eat sardines for dinner? Used to raw G, Lucy B, King and Free. So master flex, love, bug, start ski. I'm blowing up like you thought I would. Call a crib, same number, same hood. It's good. And if you don't know, now you know, you know, you know. I made this change from a common thief to up close and personal with Robin Leach. And I'm far from cheap. I smoke stuff with my piece all day. Spread love, it's the Brooklyn way. The Moet and Alizé keep me pissy. Girls used to diss me. Now they write letters but they miss me. I never thought it could happen, this rapping stuff. I was too used to packing gats and stuff. Now honeys play me close like butter play coke. From the Mississippi Delta to the East Coast. Condos and Queens. For weeks, sold out seats to hear Biggie Small speak. Living life without fear, putting 5 carats in my baby girl ear. Lunches, brunches, interviews by the fool. Considered a fool cause I dropped out of high school. Stereotypes of a black male misunderstood. And it's still all good.
Morning, everyone.
You don't know, now you know, you know. Super Nintendo, Sega Genesis. When I was dead broke, man, I couldn't picture this. 50-inch screen, money green, leather sofa. Got 2 rides, a limousine with the chauffeur. Won't feel about 2 G's flat. No need to worry, my accountant handles that. And my whole crew is lounging. Celebrating every day, no more public housing. Thinking back on my one-room shack. Now my mom lives an act with mix on her back. And she loves to show me off, of course. Smiles every time my face is up in the store. We used to fuss when the landlord dissed us. No heat, wonder why Christmas missed us. Birthdays was the worst days. Now we sip champagne every Thursday. Damn right, I like the life I live. Cause I'm projecting the positive in the soul. And if you don't know, now you know, you know, you know. And if you don't know, now you know, you know, you know.
I see.
Yeah.
All right. How are we doing this morning? Let's consider Sean's question here. Sean, I will assume the series starts at 1. You didn't mention that, but let's assume that. Of course, the question changes depending where the series starts. The convergence or divergence is not affected, right? The series will converge whether you're starting at 1 or 2 or 3 or wherever you're starting, but what the series converges to will be affected. So, as you know, here you have the sum of two things, right? And as with sequences, if both of these converge, then the sum is going to converge, and the sum of the series is the series of the sum. Name of that song, Juicy, by Notorious B.I.G. So if both converge, then the sum also converges, and the sum will converge to the sum of the two. So let's look at both of these separately, right? I mean, first of all, we don't know that the sum converges yet. We don't know that both of these converge. So let's look at each separately. What can we say about this? What can we say about this series? Well, I mean, if you treat this as 1 over e to the n, then you recognize that this is a geometric series. This is a geometric series, right? And we established the convergence of geometric series if the term is less than 1 in absolute value. But 1 over e in absolute value, right? E is 2.71 something something. So this is a number between 1/2 and 1/3. Importantly, it is less than 1. So it converges. What does it converge to? Well, you know what it converges to, right? We did that last time. This is going to converge to the first term over 1 minus a. Blah, 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 1 over e minus 1. Thank you, Joy. Thank you for the kind words. So that's the first part. What about the second part? What about the second part? 1 over n times n plus 1. Well, we actually did this exact question last time, right? You can break that up using partial fraction decomposition. This is 1 over n minus 1 over n plus 1. And you get some telescoping business. Exactly, Shamir, thank you. You get some telescoping business when you calculate the sequence of partial sums. So we did this last time and we saw that this was equal to 1. And consequently, this is going to be 1 over e minus 1 plus 1, which is e over e minus 1. May is asking how we got this thing. And this is a result we saw last time. We proved last time that the sum from k to infinity of a to the n, if a is less than 1 in absolute value, was equal to the first term over 1 minus a. That's all I'm using here. We proved that last time. This we showed last time. And here, this is a result where a is 1 over e and k is 1. So this is a to the k over 1 minus a. How are we doing? Questions? Everybody with us here? Let's tackle this one. Difficult to see, difficult to judge what's going on here. Can we rewrite this in a nice closed sigma notation form? Do we see a pattern? The 4, the 3 is maybe misleading. Let's concentrate on the other ones. You know, if you can get a general form for most of them, in other words, all but a finite few, then that's good enough, right? Why is this equal to 1 and not equal to 0? Remember that you're adding, right? So this, when n is 1, this is 1/2. Plus when n is 2, this is 2 over 3. I mean 1 over 2 times 3, so 1 over 6. And when n is 3, 3 times 4 is 12. And so on. You're adding all of these things. You're adding positive numbers. Of course, it's not going to be 0, right? Either you're going to get infinity, or you're going to get a positive number. And that number better be bigger than 1/2. And it better be bigger than 1/2 plus 1 over 6. And it better be bigger than 1/2 plus 1 over 6 plus 1 over 12, and so on and so on. Right? Each term goes to 0, and you're correct there, but we're talking about the sum of the terms. So what is happening there? And there it is. And you know, I mean, again, we did this question last time, so have a look at that if you don't remember, but we calculated the sequence of partial sums and then took its limit. Somebody's suggesting 3 to the n over 4 to the n minus 1, where n is probably going to start at 0. Right, well, I mean, Haroon had suggested 3 over 2 to the n as a first guess. And you know, I mean, you write something down and then you test it. You write out the first few terms. And if it's incorrect, then you try to adjust. So, you know, I mean, it was suggested to try this. Let's try it, see what happens. When n is 0, what is this? This is 3 to the 0 over 4 to the 0 minus 1. Sigma, so plus, when n is 1, this is 3 to the 1 over 4 to the 0. Plus, when n is 2, this is 3 squared over 4 to the 1. Plus, when n is 3, 3 cubed over 4 squared. And so on and so on. Is this correct? Let's simplify that. Do these terms match up? Three to the 0 is 1. 4 to the negative 1, you can bring this back up. So this is going to be 4. And this is 3 over 1. And this is 9 over 4. And this is 27 over 16, and so on and so on. Exactly what you had here. Very nice. So you see now, instead of working with this, we can now work with that, and that's a lot easier. What can we say about that? Right, so what can we say about that? I mean, it's looking very much like a geometric series, but not quite, right? If the -1 wasn't there, then you'd be good to go. And as Haroon suggests, very nice, right? I mean, we can take it out. This is 1 over 4 to the -1 times 3 to the n over 4 to the n, right? And you know that if you multiply these things, the exponentials add, the exponents add, and 1 over 4 to the -1 is really 4, which you can take out of the summation sign, right? This is one of the properties of series, very much like it's a property of a sequence. And a series really just is a sequence of partial sums. So this is 3 to the 4, 3 over 4 to the n. And now you recognize it as a geometric series. And as Haroon suggests, 3 over 4 in absolute value is less than 1. So a convergent geometric series. What does it converge to? Leave the 4 out there. This converges to the first term, so 3/4 to the 0 over 1 minus 3/4, which is easily seen to be 16. Right, again, without doing any work, if the series converges, it better converge to something bigger than 7. Right, and this is 2.25, so it really better converge to something bigger than 9.25. Right, because that's the sum of the first 3 terms, and you're adding positive stuff as you go along. How are we doing? Questions? Sean thought they had to be in terms of n-1 for a geometric series. Well, the book might have a different formula, different looking formula. The way we did it last time, what we did last time was we said if the series has this form, where a is less than 1, then this converges to a to the k over 1 minus a. So this is what I'm using. Yeah, so I mean, different books have different approaches, but this is the one I prefer. So for a geometric series, if the absolute value of a is less than 1, it always converges. Yes, exactly that, Sophia. And not only does it converge, but we know what it converges to. Right? It converges to this, if you're starting at k. Haroon, there's no need to introduce a line here, right? This is a 5, which does not depend on n, so it's a constant. We can take it out. And then you recognize this as a geometric series. You recognize it as a geometric series. In fact, again, this is a convergent geometric series. Since 1 over pi, 1 over 3.14159, and so on, is less than 1 in absolute value. What does it converge to? First term, 1 over pi to the 10 over 1 minus 1 over pi. Questions? Is it blurry? Looks pretty good on my end. Looks good for me. All right, consider this. Very nice, Sophia. Right, Sophia's suggesting to rewrite it as n over n plus 1, noticing that the difference between the numerator and denominator is just 1, right? So this has the form n over n plus 1, where n starts at 1. Very nice. Right, again, you write something down, maybe you want to make sure, right? I mean, have you made a mistake? So write down the first few terms. 1n is 1, this is 1 over 2. Plus 1n is 2, this is 2 over 3. Plus 1n is 3, 3 over 4, and so on. Exactly what you had before. So you know that these two things are exactly the same. And it's always easier to work with a nice closed form. What can we say about the series? Does this series converge or does it diverge? Your thoughts? Diverges, thank you, Sabiru. Why does it diverge? Right? I mean, it's easy to see that as n goes to infinity, this has the form infinity over infinity. A quick L'Hopital's rule, right? I mean, well, I'm kind of cheating here because you're not supposed to do L'Hopital's rule when dealing with n's. But of course, you know that if you take a limit as x goes to infinity, well, let's not do that. Let's factor out an n from the denominator. The n's cancel out as n goes to infinity. This goes to 0, so the limit is easily seen to be 1, and thus the series diverges by what result? Any tips on figuring out the closed form? No, no tips. It just comes with experience. My tip to you is write down what you think it is, right? I mean, you somehow have to see patterns arising and describe what's happening. So write something down and then write down the first few terms. Is it right? Are the first few terms identical to what you wanted? If they are, then you're probably correct. If they're not, then try to adjust. Because sometimes all you need is a small adjustment. Sophia's saying we cannot rewrite it as a geometric series where the absolute value of a is less than 1, so it diverges. Well, I mean, let's not go that far, right? Because yes, we have this nice result for geometric series, but not everything is a geometric series. And here you cannot rewrite it as a geometric series, so the geometric series business does not apply here. Arun would like to change it into a 1 minus 1 over n plus 1. Interesting. There's actually no need to do that. How did we get to the last line? Here I'm just evaluating the limit of the stuff we're adding. And I mean, this is a simple calculus 1 result here, but this limit goes to 1, right? I mean, if you do the limit as x goes to infinity of x over x plus 1, you can do a quick L'Hopital's rule. Quick L'Hopital's rule will give you 1. And so, thank you, Jun Chen. This series diverges by the divergence test. Right? The stuff you're adding goes to 1. So for large values of n, this is going to be very close to 1. So here it's like adding 1 plus 1 plus 1 plus 1 forever, infinitely many times. It's easy to see that you're going to get infinity. Is this divergence test and limit equal to 1 means the divergence? Exactly that, right? Divergence test tells you if the limit of the stuff you're adding is anything other than 0, the series diverges. Somebody's asking what is a geometric series exactly? Let's recall. A geometric series is a series of the form a to the n, where a is a real number. This is what a geometric series looks like. And we have a nice result that the geometric series starting at k, well, I mean, what is the result? So this is geometric series, blah, 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 and this geometric series converge if a is less than 1 in absolute value and diverge otherwise. Not only do they converge, but we know what they converge to. If a is less than 1 in absolute value, this converges to a to the k over 1 minus a. We proved that last time. If you add infinite number of ones, the series increases to infinity, exactly that. So that's why the divergence test gives you divergence. So unless the limit approaches 0, the series will diverge, exactly that. Consider this. Will we cover a Taylor series this term? That's the plan. The plan is to go all the way to Taylor series. Absolutely. It's great stuff. It's very, very, very interesting stuff. Has a bunch of useful applications. But in order to get there, we need to master series first. Because as the term suggests, Taylor series are themselves series. So before we get there, we need to know how series work. Consider this. I'm sure you have noticed. I did say there was a total of 6 Webwork. I'm going to take that back and say there's a total of 5 Webwork. There were 6, but one of them is on material that is no longer part of the curriculum. So it's down to 5. There's one more which I will open up next week. It's on sequences and series, as you can imagine. All right, consider that. But it's not that we're missing anything. It's that the material has been removed. We used to do polar coordinates and parametric curves. This is no longer part of the curriculum. It's been moved to Calculus 3. It was just too much material. It was too much material. It was a struggle to do everything. So we've removed that, and instead we're supposed to go until the end of Taylor series. It's a struggle to get there, but you know, we do what we can. Shamir is suggesting to split the sum. Shamir has obviously noticed that these are 2 geometric series, and we're good to go. We could still learn it and not have it on the exam, but the problem is that we run out of time. We just literally do not have time to do it. But you know, you can take Cal 3 and you'll learn it there. You can take Cal 3 in the summer. It's a nice summer course to do. So Shamir suggests, as you know, if both of these are convergent, which it's clear that they are, right? Because it's clear that they are 2 geometric series. And the absolute value of these things are both less than 1. So let's treat them separately. All right, let's treat them separately. Here we go. Negative 0.2 to the n. This is a geometric series. And negative 0.2 in absolute value is less than 1. So it converges. Very nice, Stefan. Maybe we'll treat that instead. So first of all, this is a geometric series where this is less than 1. So you know it converges. What does it converge to? First term. So minus 0.2 to the 1 over 1 minus 0.2. Or negative 0.2 over 1.02. So the first part convergence. And what about the second? The second, 0.6 to the n minus 1, right? Well, as it is, 1.2, thank you, 1.2, 1.2, absolutely. Right, so 0.6 to the n minus 1, the way I introduced geometric series, you really need a to the n. Somebody was suggesting, was it Matthew or Sean, or somebody else maybe, that the book has a different approach where they have the exponent to the n minus 1. I mean, whatever. Different books, internet. I mean, they're all equivalent reformulations of the same thing anyways. But the way I introduced it was you had a number to the power n. So here, either you take out the negative 1. So either you treat this as 0.6 to the negative 1 times 0.6 to the n, and then take out 0.6 to the negative 1. Or, as Stefan suggested, maybe a re-indexing would be appropriate here. And let me illustrate what I mean by that. First, let's write out the first few terms. This is 0.6 to the n minus 1, where n starts at 1. So when n is 1, it's 0.6 to the 0, which is 1. Plus when n is 2, 0.6 to the 1. Plus when n is 3, it's 0.6 squared, and so on and so on. This you can rewrite as 0.6 to the n, where n starts at 0. Right? When n is 0, that is 0.6 to the 0, which is 1. Plus when n is 1, that's 0.6 to the 1. Plus when n is 2, 0.6 squared, and so on and so on. So you see that this is really the same as this. So now let's treat this instead. This 0.6 to the n. Right, so here we're really just re-indexing. If you prefer, think of it as saying k is going to be n minus 1. So this, right, very much like a u substitution, this becomes the sum from k equals, when n is 1, k is 0. When n is infinity, k is infinity. And this is 0.6 to the k. Exactly what this means. A very useful approach. And let's finish that up. This is now a geometric series where 0.6 is less than 1 in absolute value. So you know it converges. What does it converge to? First term, minus n. All right. And consequently, our original series made up of two convergent series. This converges to minus 0.2 over 1.2. This converges to 1 over 1 minus 0.6. And so the sum converges to the sum. How are we doing? Questions? Anybody? Can we also keep the index the same and pull out a 1 over 0.6? Absolutely. Please do so, Sean. Try that. And the result should, of course, be the same. 7 over 3, I'll believe it. In this case, we would want a number. Absolutely. Absolutely. Since both of these things are geometric series, and you know the geometric series converge, and not only do you know that they converge, you know what they converge to. What about the parity of n when a is negative? What's the issue? Is there an issue? Whether a is positive or negative doesn't matter as long as that number is less than 1 in absolute value. That's where the absolute values come in for negative values of a. Let's talk about this reindexing business. Because if you remember, in the beginning of the course, I showed you a very nice proof of how to get the sum of I squared and I cubed and so on using the idea of reindexing. A very nice proof I came up with a few years ago. And wouldn't you know it, this proof also works in the case of infinite series. Let's take an example. Take a value of a which is less than 1 in absolute value. So we're taking a to be less than 1, and if you reindex, this is really the sum from 1 to infinity of n a n. Right? I mean, convince yourselves. This is this business when n is 0. This is 1 a to the 1. So that's just a. Plus when n is 1, this is 2a squared. And when n is 2, this is 3a cubed. In this business, when n is 1, this is a. Plus when n is 2, this is 2a squared. And when n is 3, this is 3a cubed. And so on and so on. You see that they're the same thing. Right? So this series is equal to that series. But by properties of series, this this is NA to the n plus 1 plus A to the n plus 1, assuming both converge. And here, take out an A, so this is A and AN. And this, again, take out the A. And when n is 0, this is 0 times A to the 0, so 0 times 1, which is 0. So the first term is 0. So this, you can really make it start at 1, because it doesn't matter if you're adding 0 or not. And this, well, this is a convergent geometric series, right? Because A is less than 1. So this converges to 1 over 1 minus A. And now, in very much the same trick as with the integral of secant cubed, or the integral of e to the x sine x, where after integrating twice, you end up with the same thing on the right, and you bring it over to the other side. This is equal. These two things are equal. All right, let's rewrite that. What are we saying? And A to the n is equal to A and A to the n plus A over 1 minus A. So if you bring this to the other side, and if you factor out this sum, you see that the sum is equal to A over 1 minus A all squared. Isn't that amazing? And this idea generalizes. If you square this, and then you expand that, that would be n squared plus 2n plus 1, and you can get, what is this still 11.2? The problem is this isn't in the book. This is something I came up with. Nobody knows about this except you. Exactly. Exclusive content. That's why you're paying the big bucks. All right. How are we doing? All right. Consider this. Right? right? So I mean, what I'm suggesting here, in the same way that we prove this, you can prove what n squared, a to the n converges to, and n cubed, and n to the 4, and so on and so on. That was a proof, yes. Absolutely. The only assumption that was made here is that this series actually converges. We're actually not in a position to prove that yet. We will be able to prove that in half an hour. Half an hour seems optimistic now. Right, and of course, nobody's fazed by that. Don't let K fool you, whether it's N or whether it's K, it's just a dummy variable. So absolutely nothing to worry about, as Zoe was pointing out. How do we tackle this? How do we establish the convergence or divergence of this series? Of course, you recognize that it is not a geometric series, right? It's not a number to the power k. How do we answer that? You know how to answer that. Divergence. Absolutely. Divergence test. The limit as k goes to infinity right? This has the form infinity over infinity. If you switch to x, you can use L'Hopital's rule, or if you leave it in k, you can just factor out exactly right. These cancel out. As k goes to infinity, this goes to 0, that goes to 0, so the whole thing goes to 1. And thus the series diverges by the divergence test. Right? On an exam, all of this has to be shown and spelled out, right? Just because you take this limit doesn't mean that the marker knows what you're doing, right? I mean, it's obvious to you that you're doing the divergence test, but please justify that in the end. So the series diverges by the divergence test, since this is not 0. Well, I mean, spell it out. So Omar is asking what I mean by justifying in the end, right? Just taking the limit isn't enough, because it might not be clear to the marker what you're actually doing. So you took a limit, you notice that it was not 0, and consequently, you should say the series diverges by the divergence test. Why does it matter that the limit doesn't equal 0? Exactly, Sophia, and that's exactly why we have to justify. The divergence test tells us that if the limit is not 0, then the series diverges. If the limit of the stuff you're adding is not 0, the series diverges. Right here, the limit is 1, so think about what's happening here. For large values of k, this is like adding 1 plus 1 plus 1 plus 1 infinitely many times. You're going to get infinity. Convinced? Consider this. You see what's happening here, right? You see that here you have a geometric series. How many different tests will we learn? Many, but not that much, maybe 7 or something, 7, 8-ish. A better question is how many different tests are there? And the answer is hundreds of tests out there. We're only going to look at I don't want to say more important ones, but let me say it. We'll only look at the more important ones, but I mean, some are so pointy that you can essentially only use them for 1 or 2 series. If only one term of the series diverges, do we have to show the others, or can we stop there? Well, that's again an excellent question, right? You recognize here that here you have a convergent geometric series, but then you have a divergent series here. This one diverges, right? I mean, again, we showed that last time. So a question arises now. If you have a convergent series and a divergent one, is the sum necessarily divergent? And that's actually what question 89 is asking. If one series converges and one series diverges, show that the sum diverges. So let's do it in general. Let's prove 89, which will completely answer number 48. Right, and then you'll be able to use this result from now on. If you have one series which converges and another one which diverges, the sum will have to diverge. And the proof is very nice. It's one line. Does the sum of 2 divergent series necessarily diverge? And that's an excellent question. I'm going to let you think about that. We'll prove this one first, and then we'll answer that question. So think about that question. If you have 2 divergent series, does the sum necessarily diverge? We did not cover Simpson's rule, so no worries. Proof by contradiction. Suppose the sum converges. Suppose the sum converges. Then, since the sum of AN converges as well, then you can add or subtract the 2 and get a convergent series. Right? Because if you have 2 convergent series, then their sum converges or difference, right? But that is the series Bn, which you knew to diverge. Contradiction. Very nice and slick, right? You suppose the contrary, and quickly you get a contradiction. So if you have a convergent series and a divergent one, the sum must diverge. So here, three over 5 to the n, which is 3 times 1 over 5, the whole thing to the n, is a convergent geometric series where 1 over 5 in absolute value is less than 1. And the series 1 over n diverges. We showed that last time. So the sum of a convergent series and a divergent one diverges. Do these two arrows mean proof by contradiction? Well, I mean, it means you get a contradiction, right? This series has to converge, which contradicts, I mean, I've rubbed it off now, but it contradicts the assumption that this was a divergent series. How do we do it? Questions? On the exam, you can assume the series 1 over n diverges. I was planning to do a bit more than what we're actually doing today, and I was going to give you a result where you were going to remember that the series 1 over n diverges without thinking anymore, right? I mean, we proved it last time using the sequence of partial sums, but we're going to see it again very soon. Maybe by the end of the day, if we can manage. Let's do a nice example here. So sigma bn diverges. That was in the assumption, right? We had sigma an converges and sigma bn diverges, and we wanted to show that the sum diverges as well. So if we just show one converge and the other diverges, we can know their sum diverges. Yes, absolutely. Just refer to that theorem. Actually, before we look at 54, somebody had asked, what if you have two divergent series? Does the sum necessarily diverge? That was Jacob. Do we have an answer to that? Two divergent series. Does the sum necessarily diverge? Let's make it simpler. What if you had sequences? What if you had two divergent sequences? Does the sum necessarily diverge? What if you had two functions where the limits was infinity? Matthew is suggesting no, you might get an infinity over infinity. Make it simpler, simpler, simpler. Give me a series which diverges. Well, I mean, we have one right here. Series 1 over n diverges. So the series negative 1 over n also diverges. And when you, exactly right, as Selena is suggesting, and when you add them together, you you get the series of 0, which converges. Because 0 plus 0 plus 0 plus 0 is 0. There it is. How are we doing? Convinced? 54 is a nice question here. Because, in high school, you learn that the rational numbers denoted by Q. What do you learn in high school? You learn that rational numbers are numbers whose decimal expansion either terminates or repeats. So this is the set of numbers whose decimal expansion terminates or repeats. Well, I don't know if you're still learning that in high school, but at least that's what I learned back in the day. So in high school, we were told that the rational numbers are the set of numbers whose decimal expansion either terminates or repeats. And then when I got to university, suddenly it was a whole new definition. Suddenly, the rational numbers were the set of fractions. Right? Set of fractions of integers. And not a single word was said from then on. Well, it's not immediately clear that these two things are the same. If you take a number whose decimal expansion terminates, like 0.123, then of course this is 123 over 1,000. So you've written it as a fraction of integers. That's very easy. But what if the decimal expansion repeats? It's not immediately clear that this is necessarily a fraction of integers. The number 54 is asking us to express to do exactly that. Express 0.56, 0.46, 46, 46, where the 46 repeats as a fraction of integers. Well, what is that? This first 46 is really 46 over 100. And this next 46 is really 46 over 10,000. And this next 46 is really 46 over a million. And so on and so on. And this 10,000 is really 100 squared. And this million is really 100 cubed. And so on and so on. And we can rewrite this in a nice, simple, closed form. If you take the 46 out, can we rewrite this in terms of sigma notation? 1 over 100, 1 over 100 squared, 1 over 100 cubed. I think you know where we're going with that, right? 1 over 100 to the n, where n starts at. Where n starts at 1. And this is a convergent geometric series. Where 1 over 100 is less than 1. What does it converge to? First term. I'm running out of room here. Thank you, Taha. Exactly right. What does it converge to? 46 out front. First term, 1 over 100, over 1 minus 1 over 100. So this is 46, 1 over 100, over 99 over 100. The hundreds cancel out. 46 over 99. If you do 46 divided by 99 on a calculator, you'll see that you get 0.46, 46, 46, and so on. Very nice exercise. Let's do another one. Let's try another one. Same question, but 0.99999 where the 9 repeats. Right? Thank you, Michael. We can easily see that this is 9 over 10 plus 9 over 100 plus 9 over 1,000 and so on, right? Or 9 over 10, 9 over 10 squared, 9 over 10 cubed, and so on. If you rewrite this as in a nice simple closed form, 9 over 10 to the n, right? When n is 1, you get this term. When n is 2, you get 9 over 100, 9 over 10 cubed, and so on, right? So it's easy to see that these two things are equal. Factor out the 9. And this is a nice geometric series, a convergent geometric series again. Where 1 over 10 in absolute value is less than 1. What does it converge to? First term, so 1 over 10, over 1 minus 1 over 10. So 9 times 1 over 10, over 9 over 10. The 10's cancel out, and you get 9 over 9, which is 1. the number 0.999, where the 9 repeats, is equal to 1. Isn't that amazing? Yep, exactly that. The number 0.99999, where the 9 repeats, is equal to 1. Well, I mean, doesn't this break math? What are the implications of that? Right? I mean, you're used to writing things and not worrying about it. What do I mean by that? I mean, if you have 3 apples, then the only way to represent 3 is this way. And you write 3 down and you don't think about it anymore. That's the answer. But there's another way to represent 3, right? 3 is really 2.999, where the 9 repeats. So numbers don't have a unique representation. The number 2.99999 is the same as the number 3. And exactly as Graham suggests, one way to convince yourself is that if you think of it as being on a number line, then, since it's 0.9 something something, it has to be somewhere to the left of 1. But it has to be bigger than 0.9, so it has to be somewhere in here. And it has to be bigger than 0.99, so it has to be something in here. And you can keep making that interval so small that it can't be anything less than 1. Exactly that. Okay. All right. Questions here? So that's one very nice result that follows from series. Now, think back to improper integrals. Right? In improper integrals, where we were integrating over an infinite region, we were asking the question, does the function go to 0 fast enough so that this area is actually finite? And in series, we're kind of doing the same thing. So the obvious question arises, is there a relationship between improper integrals and infinite series? And that's what we'll discuss next week. Thank you all for coming, folks. You guys have a good weekend. And I will see you then. Questions before we end? Right, I mean, it is a very nice result, which is unexpected, we'll see more unexpected results in the weeks to come. This series business really is amazing. You get incredible results. We'll pick this up again next week. You guys have a good one. I will see you on Tuesday.